chapter Real Numbers.
This slide presents the overview of the chapter.
Learning objectives. By the end of this chapter, you will be able to identify rational and irrational numbers, state fundamental theorem of arithmetic, explain decimal expansions, prove irrational numbers, state laws of logarithms.
Introduction. Before entering into the chapter, follow the instructions shown on the screen. Click each tab to know more.
We learned from previous classes that natural numbers are the set of numbers which start from 1. They are denoted by n. Example, n is equal to 1, 2, 3, so on. Whole numbers are the set of numbers that include 0 along with the natural numbers. They are denoted by W. Example, 0, 1, 2, 3, and so on. An integer is a whole number that can be positive or negative or 0, but it should not be a fractional number. It is denoted by letter Z. For example, Z is equal to -3, -2, -1, 0, 1, 2, 3, and so on. Now, let us recall about rational and irrational numbers. Rational numbers are the numbers that can be expressed in the form of P by Q, where P and Q are integers, and Q not equal to 0. They are denoted by Q. Always, rational numbers are expressed by using terminating decimals or non-terminating repeating decimals. Examples of rational numbers are as shown on the screen. Finally, we conclude that rational numbers contain the set of natural numbers, whole numbers, and integers. We also have irrational numbers which cannot be expressed in the form of P by Q, where P, Q are integers and Q not equal to 0. Some of these numbers are √2, √3, and mathematical quantities like pi. When these are written as decimals, they are non-terminating and non-recurring. You know that rational numbers contain the set of natural numbers, whole numbers, and integers. But do you know that rational numbers are contained in some other set of numbers? Let us learn about various properties of rational and irrational numbers in details, and also about logarithms.
Do you want to make money, but can't find a way of make money? Download the app. Enjoy the best value for money. Yeah.
Let us know about Euclid's division algorithm. The algorithm name itself suggests us to do with divisibility of integers. It simply states that if any positive integer x is divided by another positive integer y, then it gives remainder z, which is smaller than y. Let us do an example. Suppose if x is equal to 22, y is equal to 5, then the remainder z equal to 2, which is smaller than y. The result obtained by division process is quite easy to understand, but it has got many applications relating to divisibility properties of integers. Let us learn few of them which are mainly used to calculate HCF of two positive integers. Now, let us learn about Euclid's division lemma by considering a puzzle. A trader was moving along a road by selling cups. An idler who did not have much work to do started to get the trader into a wordy duel. This grew into a fight. He pulled the basket with cups and dashed it on the floor. The cups broke. The trader requested the panchayat to ask the idler to pay for the broken cups. The panchayat asked the trader how many cups were broken. He gave the following response. If counted in pairs, 1 will remain. If counted in threes, 2 will remain. If counted in fours, 3 will remain. If counted in fives, 4 will remain. If counted in sixes, 5 will remain. If counted in sevens, nothing will remain. My basket cannot accommodate more than 150 cups. How many cups were there? Let us try to solve the puzzle and find how many cups were there in the basket. Solution. Let the number of cups be A. From the given problem, if we observe it from the last, we can say that A less than or equal to 150. Since the basket can accommodate either 150 cups or less than 150 cups, but not more than that. 1. If A is divided by 2, 3, 4, 5, 6 each time, then we know that the remainder in each case is 1 less than the divisor. That is, A is 1 less than the LCM of 2, 3, 4, 5, 6. Now, LCM of 2, 3, 4, 5, 6 is 60. Therefore, A can be 60 minus 1, 120 minus 1, 180 minus 1, and so on. 2. If A is divided by 7, nothing will left given. That is, A is divisible by 7. 60 minus 1, that is 59, is not divisible by 7. 120 minus 1, that is 119, is divisible by 7. Therefore, A can be 119. 3. The trader basket cannot accommodate more than 150 cups. Therefore, 180 minus 1 cups cannot be there. Therefore, number of cups broken is equal to 119. To understand the Euclid's division lemma more clearly, let us do the problem by considering following pair of integers. A. 28. B. 17, 5. Consider a bit that is 20 and 8. Here A is equal to 20, B is equal to 8. Thus, by applying the Euclid's division lemma EDL to the above numbers, we obtain as follows. Here we know that A is equal to BQ plus R. So when 20 is divided by 8, we obtain quotient Q as 2 and remainder R is equal to 4. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal. Similarly, let's consider second set of numbers 17 and 5. Here, A is equal to 17, B is equal to 5. Thus, by applying the Euclid's division lemma EDL to the above numbers, we obtain as follows. Here we know that A is equal to BQ plus R. So when 17 is divided by 5, we obtain quotient Q as 3 and remainder R is equal to 2. Substituting the obtained values of Q and R in the above expression, we obtain both LHS and RHS equal.